Myself, Mrs. Maya Pramod, PGT Chemistry, KV number 2, Agra, Kent. It's very clear that we are going to study about classification of elements and periodicity and properties. This is third chapter in NCERT of class 11. CBSE has revised curriculum for the session 2020-21 due to COVID-19 pandemic. Some portions has been deleted or we can say reduced. They are significance of classification, brief history of development of periodic table. As all this you have already studied in your class 10th. The portions to be studied are modern periodic law and the present form of periodic table, periodic trends in the properties of elements like atomic radii, ionic radii, van der Waals radii, ionization enthalpy, electron gain enthalpy, electronegativity, valence electron, valency, metallic and non-metallic character and their reactivity across the period and down the graph. Lastly, nomenclature of elements with atomic number greater than 100. Although all these elements have been discovered and official name has also been given to them, but still we should know how to do naming of elements with atomic number greater than 100 as per IUPAC norms. Let's recapitulate what all we have studied in our class 10. Law of triads. According to de Bruyn's law of triads, the properties of the middle element were in between those of the other two members. The elements were arranged in a group of 3 called triads. The atomic weight of a middle element was almost the average of the other two. The 3 elements of triad had similar chemical properties, but only 3 triads could be formed, hence it was rejected. Newland's law of octave. The elements were placed in increasing order of their atomic weights, and it was noted that every 8th element had properties similar to the first one. The relationship was just like every 8th note that resembles the first in octave of music. For example, sa, re, ga, ma, pa, dha, ni, sa. This is the again 8th sargam which gets repeated. Newland's law of octave seemed to be true to the elements only up to calcium. Mendeleev, known as father of periodic table, gave the law Mendeleev's periodic law, which states that the properties of elements are periodic function of their atomic weight. Mendeleev arranged elements in horizontal rows and vertical columns of a periodic table in order of their increasing atomic weights in such a way that the elements with similar properties occupied the same vertical columns or the group. Hence, we can say the vertical columns are known as group, whereas the horizontal rows are known as period in a periodic. Merits of Mendeleev's periodic table. Given more weight to similarities in properties than to atomic mass in the arrangement. Correction of atomic masses of some elements. Prediction of new elements. Mendeleev left gap under silicon and aluminium, which can be seen from this table. Silicon, the Ica silicon, new element, and properties were similar to germanium. Under aluminium, Ika aluminium, properties were similar to that of gallium. Now the drawbacks or the demerits of Mendeleev's periodic table. Hydrogen's position could not be explained very well because hydrogen resembled the properties of both alkali metals and that of halogens. Hence, the position of hydrogen, whether hydrogen is to be placed with halogen or alkali metal, was not specified. Position for isotopes. Isotopes are those with same atomic number but different mass numbers. Mendeleev's periodic table was based on arranging elements in increasing order of atomic masses, but isotopes were not included in his periodic table. Lastly, certain elements were arranged in reverse order. Elements having higher atomic masses were placed in front or before the elements with lesser atomic mass. For example, cobalt and nickel. Cobalt, being more heavier than nickel, was placed before nickel in the Mendeleev's periodic table. These were the drawbacks of Mendeleev's periodic table. The learning objectives of this chapter are modern periodic law and the present form of periodic table, that is, the long form of periodic table, classification of elements in SPDF blocks on the basis of electronic configuration, general characteristics of elements in SPDF block, periodic trends in properties of elements like atomic radii, ionic radii, metallic radii, ionization enthalpy, electron gain enthalpy, electronegativity, valency, etc. Anomalous behavior of second period elements because they are the first member in their respective group. Finally, the diagonal relationship between the elements of second period with the elements of third period, which are diagonal to each other. Nomenclature of elements with atomic number greater than 100. Dmitri Mendeleev, known as father of periodic table, formulated the periodic law, created a far-sighted version of periodic table of elements and used it to correct the properties of some already discovered elements, and also predicted properties of 8 elements yet to be discovered. But his periodic table was further perfected by Henry Moseley by taking atomic number into consideration. He could remove some of the anomalies of Mendeleev's periodic table by taking into consideration atomic number as fundamental basis for the properties of elements. He formulated modern periodic law and the present form of periodic table. The modern periodic law states that the physical and chemical properties of the elements are periodic function of their atomic numbers. The long form periodic table arranges elements based on their atomic numbers and outer electronic configuration. In long form periodic table, there are 7 periods, 18 groups. Periods are horizontal rows and groups are the vertical columns. Elements having same principal quantum number are arranged in periods, whereas elements with similar outer electronic configuration are arranged in groups. long form periodic table. Here we can see there are 18 groups and 7 periods. The distribution of electrons into the shells and the orbitals of an atom is called its electronic configuration. Now we know that the electronic configuration of an atom is very important as it defines its physical and chemical properties. The elements in the long form periodic table are organized based on the principal quantum numbers of the last filled orbitals. Hence, we can see that electronic configuration of element is correlated with the periodic table. Electronic configuration of elements in a period, how they are correlated with the principal quantum number. Let's try to understand it. From the table, we can see that the period number depends upon the principal quantum number, that is, in which the last electron enters. And the number of elements in a particular period depends upon the total number of electrons in the orbitals. Here we can see in the period first, the electron enters only in the s orbital, which can accommodate only 2 electrons. Hence, the number of elements in period 1 are 2. The first element is hydrogen and the last element is helium. Similarly, if we see period 2, the electron enters in 2s and 2p orbitals. Total 2 plus 6, 8 electrons can be accommodated, and hence the number of elements present in this period are 8. The first member is lithium with 2s1 configuration, and the last element is neon with 3s2, 3p6 configuration. In period 3, again, electron enters in s and p orbital, but the principal quantum number is 3. Total number of elements in this period are 8, as total 8 electrons can be accommodated in s and p orbital. The first member is sodium and the last member is argon. As we move down in the fourth period, we observe that electrons are filled in s, p and d orbital. The total number of electrons in s and p orbital are 8. Now 10 electrons can be accommodated in d orbital. So 8 plus 10, total 18 elements are present in fourth period. First element potassium and the last element is krypton. Similarly, in period 5, the principal quantum number changes to 5, but electron enters in s, p and d orbital. Total 18 elements in this period. First element rubidium and the last element xenon. Coming down to the sixth period, electron enters in f orbital besides d, s and p orbital. Now, the total electron which can be filled up in all these orbitals are 2 plus 14, 16, 16 plus 10, 26 plus 6, 32, and hence we can see that there are 32 elements in this group. The first element cesium and the last element radon. Similarly, in the seventh period, electron enters in S, P, D and F orbital. So total 32 elements are present. The first element being francium and the last element being oganesson. The number of elements in the period is 2 times the number of atomic orbitals available in the energy level that is being filled. Therefore, the 7 periods contain 2, 8, 8, 18, 18, 32, 32 elements respectively. This is also known as magic number. Here we can see number of elements in a particular period. 2 elements in period 1 as electron enters only in s orbital. 8 elements in period 2, 8 elements in period 3 as there are s and p orbitals, 1s and 3p. 18 elements in period 4, 18 elements in period 5. Here, electrons are filled in 9 orbitals, 1s, 3p and 5d, altogether 9. Now 32 elements in period 6 and 32 elements in period 7, because here there is entry of f orbital. So 1 s orbital, 3 p orbital, 5 d orbitals and 7 f orbitals. Together it becomes 16. So 16 twos are 32. General outer electronic configuration of elements and groups. From this table, it's very clear that elements in a particular group has same electronic configuration, and the configuration for elements belonging to various groups from 1 to 18 is given here along with the F block elements. We can conclude the elements in the same vertical column or groups have similar valence shell electronic configuration, same number of valence electron, and therefore they show similar properties. Hence, on the basis of electronic configuration, the periodic table is divided into 4 blocks depending upon the entry of last electron in a particular orbital. The 4 blocks are S, P, D and F. Classification of elements in S, P, D, F block is done on the basis of electronic configuration. From this table, we can see that periodic table is divided into 4 blocks S, P, D and F. NS12 is the general electronic configuration of S block element, and the last electron enters in s orbital. They are usually metals, also known as representative elements. NS2 NP126 is the general electronic configuration of p block element, where the last electron enters in the p orbital. They include metals, nonmetals and metalloids, also known as representative elements. NS-1, D 1 to 10 and NS12 is the general electronic configuration of D block. They are metals, also known as transition elements, present in between S and P block. F block general electronic configuration is N-2 F 1 to 14, N-1 D 01, Ns2. They are mostly radioactive in nature, also known as inner transition elements because they are present within the transition elements. As proper place is not there in the main periodic table, they have been placed at the bottom of main periodic. Now, characteristics of S block elements. The elements of group 1, also known as alkali metals, and group 2, also known as alkaline earth metals, which have Ns1, Ns2 outermost electronic configuration, are included in S block elements. The S block elements are called representative elements or main group elements. They are all reactive metals with low ionization enthalpies. They lose the outermost electrons readily to form +1 ion in case of alkali metals or +2 ions in case of alkaline earth metals. The metallic character and the reactivity increases as we go down the group because of high reactivity. They are never found in pure state in nature. The compounds of S block elements, with exception of those of lithium and beryllium, are predominantly ionic in nature. They are good conductor of heat and electricity, with exception of hydrogen and helium. They are silvery, shiny metallic substance, with the exception of hydrogen and helium, which is gaseous nonmetal. They are malleable and ductile, that is, we can make sheets and wire from them. Again, hydrogen and helium are the exceptions. They readily form ionic salts with most non-metals. Aqueous solution of their oxides are alkaline in nature. Characteristics of P block elements. They include group 13 to 18. P block elements are called representative elements or main group elements. The outermost electronic configuration varies from Ns2 Np 1 to 6. At the end of each period, that is group 18, is a noble gas element with closed valence shell Ns2 Np6 configuration. All the orbitals in valence shell of the noble gases are completely filled by electrons, thus exhibit very low chemical reactivity. Preceding the noble gas family are two chemically important groups of non-metals. They are halogens, group 17, and chalcogens, group 16. These two groups of elements have highly negative electron gain enthalpies and readily add 1 or 2 electrons respectively to attain the stable noble gas configuration. The non-metallic character increases as we move from left to right across a period, and metallic character increases as we go down the group from top to bottom. Here, helium is again an exception in group 18 because it is not having Ns2 Np1 to 6 configuration, but it is having Ns2 configuration where s orbital is completely filled. Characteristics of D block elements. Elements of group 3 to 12 are included in D block elements, known as transition metals. Outer electronic configuration N-1 D1 to 10 NS12. 4 transition series are 3D, 4D, 5D and 6D. They are metals used as catalysts, shows variable oxidation states, forms colored compounds, are paramagnetic in nature, form alloys. Characteristics of F-block elements. Elements in which the f orbital is completely filled are called F-block elements. The general electronic configuration is Ns2, N-1d 0 to 1, N-2f 1 to 10, known as inner transition metals. They have incomplete d orbital electronic configuration in their normal state and in their oxidation state. They are generally radioactive. Lanthanoids and actinoids are 2 series. Periodicity and atomic properties. Periodicity is the repetition of similar properties after regular intervals. Cause of periodicity. The properties of elements are periodic repetition of similar electronic configuration of elements as the number, that is atomic number, increases. Atomic properties are the physical characteristics of the atoms of an element. The properties such as atomic radius, ionic radius, ionization energy, electronegativity, electron gain enthalpy are known as atomic properties. Atomic properties of elements. Metallic radii, covalent radii, van der Waals radii, ionic radii, ionization enthalpy, electron gain enthalpy, electronegativity are to be studied. Atomic radius. Since atoms are very small, very small, atomic radius of individual atom can't be measured. Hence, we need to measure metallic radius, covalent radius or ionic radius. Here we can see these are the two atoms of metals in close contact with each other. Half of the distance between the nuclei of two adjacent metal atoms in a closed packed lattice of the metal is called its metallic radius. Hence, this is the one way to measure the atomic radius by measuring metallic radius. Here we can see that the molecule is covalently bonded due to the sharing of electron. This represents the bond length, that is internuclear distance between the two bonded atoms. And half of the bond length is known as covalent radius. Hence, covalent radius is half the internuclear distance between two similar atoms of an element which are covalently bonded to each other by a single covalent bond. This is one covalently bonded molecule. This is the another covalently bonded molecule closer to each other. The distance AB is the internuclear distance between the covalently bonded molecule in close vicinity to each other, and half of this distance, that is AB by 2, is known as van der Waals radius. Hence, half the internuclear separation between two similar adjacent atoms belonging to the two neighboring molecules of the same substance in the solid state is called the van der Waals radius of that atom. If we compare van der Waals radius, metallic radius and covalent radius, we find that van der Waals radius is always greater than metallic radius, which is greater than covalent radius. Ionic radius of an element is the element's share of distance between neighboring ions in an ionic solid. Ionic solids usually contain cation and anions, and cations are smaller than their parent atoms, anions are larger than their parent atoms. This distance is known as radius of anion, whereas this is known as radius of cation. Here, from this figure, we can very well see as we move from left to right, the size of atom it goes on decreasing, whereas when we move from top to bottom, the size of atom increases. Reason can be understood with this diagram. From left to right, what happens? Atomic size decreases. Why? Because electrons are added in the same shell. There is increase in effective nuclear charge. On the other hand, on moving down from top to bottom in a group, atomic size increases because there is increase in the number of subshell and decrease in the effective nuclear charge. In the periodic table, we can see how atomic size varies across the period and down the graph. Across the period, when we move from left to right, we can see that atomic size decreases. On moving down in the graph, atomic size increases. This is the trend of atomic size in the periodic table. Now here we can see the neutral atom. Either it can lose electron or it can gain electron. When it loses electron, it results in the formation of cation, and on gain of electron, it results in the formation of anion. From this figure, we can very well see that the neutral atom, it has lost electron to form a cation, and the size of cation is comparatively smaller than that of parent atom. The reason being, for same nuclear charge, now number of electrons are less. As a result, there is more attraction between electron and the nucleus. Here we can see the neutral atom. It has gained electron, and on gaining electron, the nuclear charge was same, but due to extra electron, now the attraction between, or the force of attraction between electron and the nucleus decreases. As a result, there is repulsion between incoming electron and the electrons which are already present. It results in increase in the size. Now during this loss or gain, there are chances that the anion or cation, they may have same number of electrons, and such species are known as isoelectronic species. Hence, we can say isoelectronic species are species having same number of electrons. What we can conclude is the cations with greater positive charge has smaller radii. On the other hand, the anion with greater negative charge has larger radii. Isoelectronic species and variation in their size can be well explained and understood with following example. Sodium, magnesium, aluminium, nitrogen, oxygen, fluorine are the elements which we have taken into consideration with atomic number 11, 12, 13, 7, 8, 9 respectively. Sodium, magnesium, aluminium are metals, hence they will lose electron, whereas nitrogen, oxygen and fluorine, they are non-metals, they will gain electron to acquire inert gas configuration. Let's see what happens. Sodium forms sodium ion, magnesium forms Mg2 positive, aluminium Al3 positive, nitrogen N3 negative, oxygen O2 negative and fluorine F negative. Now the nuclear charge in all these ions are 11 in Na positive, 12 in Mg2 positive, 13 in Al3 positive, 7 in N3 negative, 8 O2 negative, 9 F negative. What happens to the number of electron now? All of them have 10 electrons. Hence, they all are known as isoelectronic species. From here, one thing is clear. For same number of electrons in this species, the nuclear charge is different. And more the nuclear charge, more will be the attraction between electron and the nucleus. Lesser the nuclear charge, lesser will be the attraction between nucleus and the electron, and this will result in the variation of size. Let us see. Sodium ion, magnesium ion, aluminium ion, nitrogen ion, oxygen ion, fluoride ion. From left to right in these cations, we see that sodium ion is having larger size as compared to other two ions, and aluminium is the smallest in size because it is having more positive charge. In case of these anions, we can see that nitrogen is bigger in size, nitrogen ion is bigger in size, and fluoride ion is isoelectronic species with 10 electrons are as follow. Aluminium 3 positive with 13 proton, magnesium 2 positive with 12 proton, sodium 1 positive with 11 proton, F negative with 9, O2 negative with 8, N3 negative with 7. we can see that the size is increasing as we are moving from left to right for the isoelectronic species because of decrease in the nuclear charge. So this is how isoelectronic species are arranged in increasing order. Now case is reverse. N3 negative with 7 proton, O2 negative 8 proton, F negative 9 proton, Na positive 11 proton, Mg2 positive 12 proton, and Al3 positive with 13 proton. Here the number of electrons in all these ions are same, that is 10. But we can see the arrangement. Now they are arranged in decreasing order of their size. This is how arrangement of isoelectronic ions are placed in decreasing order of size. The next atomic property is ionization enthalpy. Ionization enthalpy is the amount of energy required by an isolated gaseous atom to lose an electron in its ground state. Thus, enthalpy change for the reaction M gas changes into M positive gas by loss of an electron. The energy required to remove this one electron or the first electron is known as ionization enthalpy. The electrons are removed one by one. We can see M positive changes into M2 positive by removal of another electron. Now the ionization enthalpy is known as successive ionization enthalpy or second ionization enthalpy. Ionization enthalpy is expressed in kilojoules per mole or in electron volt. Now factors which influence ionization enthalpy: atomic size, effective nuclear charge, penetration effect of orbitals, shielding or screening effect, stability of half-filled and fully filled orbitals. Atomic size is the first factor that affects ionization energy. There is inverse relation between ionization energy and atomic size. The larger the size of the atom, smaller is the ionization energy. Smaller the size of atom, larger the ionization energy. From this figure, it's very clear. As we move from left to right in the period, the atomic size decreases, hence ionization enthalpy increases. As we move down from top to bottom in the graph, the atomic size increases and ionization energy decreases. The next factor is effective nuclear charge is the another factor. The effective nuclear charge, often symbolized as Z effective or Z star, is the net positive charge experienced by an electron in a multi-electron atom. The term effective is used because the shielding effect of negatively charged electrons prevents higher orbital electrons from experiencing the full nuclear charge. The effective nuclear charge on an electron is given by following equation. Z effective is equal to Z minus S, where Z is the number of proton in the nucleus, that is atomic number, and S is the number of electrons between nucleus and the electrons in question, that is the number of non-valence electron, or we can say the number of electrons between nucleus and the valence shell. Effective nuclear charge is given by the equation Z effective is equal to Z minus S, where Z is the atomic number, S is the number of inner electrons. Here we can see that the nucleus has 11 proton and the valence electron is 1. In between valence electron and the nucleus, the inner electrons are 10. Hence, the combined effect can be given as Z is equal to 11 minus 10 equals to 1, which is the total effective nuclear charge. Stability of half-filled and fully filled orbitals also play an important role. According to Hund's rule, the stability of half-filled or completely filled degenerate orbitals is comparatively high, so more energy is required to separate the electron from such atoms. Reason? The symmetrical distribution of electron, the exchange energy. We can see here that there are 4 exchanges by electron 1, 3 by electron 2, 2 by electron 3 and 1 by electron 4. In periodic table, how ionization enthalpy varies in period and group. On moving from left to right in period, the ionization enthalpy increases, whereas on moving down from top to bottom in group, ionization enthalpy decreases. This is the trend of ionization enthalpy in periodic table. Electron gain enthalpy. The electron gain enthalpy is the molar enthalpy change when an isolated gaseous atom or ion in its ground state adds an electron to form the corresponding anions. Thus, the enthalpy change for the reaction X in gaseous state gains an electron to form anion X negative in gaseous state, and the enthalpy change is known as electron gain enthalpy of the element X. For example, X by gaining electron changes into X negative. Here it has gained the first electron, and this enthalpy change is known as first electron gain enthalpy or simply electron gain enthalpy. But when second electron gets added up to X negative to form X2 negative, then this electron gain enthalpy is known as second electron gain enthalpy. Similarly, when third electron gets added up, then the enthalpy change is known as third electron gain enthalpy. Now, this electron gain enthalpy may be either positive or negative. Negative when energy is released while accepting an electron, and positive when energy is supplied to an atom while adding an electron. Let's try to understand. Here we can see these are the elements belonging to halogen family, that is group 16. Being smaller in size, they have more tendency to attract the outer electron to get converted into anion. Hence, they have negative electron gain enthalpy. Whereas helium, neon, argon, krypton, xenon, radon, they are all inert gases. Now, for addition of an electron, an extra shell is required because their outermost shell is already having 8 electrons. Hence, energy is to be supplied and the electron gain enthalpy becomes positive. Factors affecting electron gain enthalpy: atomic size, nuclear charge, electronic configuration. As the size of atom increases, the distance between the nucleus and the last shell, which receives the incoming electrons, increases. This decreases the force of attraction between the nucleus and the incoming electron. Hence, electron gain enthalpy becomes less negative. Nuclear charge. As the nuclear charge increases, the force of attraction between nucleus and the incoming electron increases. Hence, enthalpy becomes more negative. Electronic configuration also plays an important role. Elements with exactly half-filled or completely filled orbitals are very stable. You have to supply energy to add an electron. Hence, their electron gain enthalpy has large positive values. The electron gain enthalpy becomes less negative in going from top to bottom in the group, and it becomes more negative in going from left to right in a period. In periodic table, let's sum up electron gain enthalpy. On moving down in the group from top to bottom, electron gain enthalpy decreases, metallic character increases, and non-metallic character decreases. In period from left to right, electron gain enthalpy increases, metallic character decreases, and non-metallic character increases. This is the trend of electron gain enthalpy in periodic table. Electronegativity. The relative tendency of an atom in a molecule to attract the shared pair of electrons towards itself is termed as its electronegativity. From this figure, we'll try to understand the concept. This is the shared pair of electron between hydrogen and chlorine in HCl molecule. Chlorine experiences strong pull, whereas hydrogen experiences weak pull. As a result, shared pair of electron is taken away by chlorine. A positive charge develops on hydrogen and negative charge develops on chlorine. Factors affecting the magnitude of electronegativity are atomic radius, effective nuclear charge, oxidation state of the atom, hybridization state of an atom in a molecule. Atomic radius. As the atomic radius of the element increases, the electronegativity value decreases. Effective nuclear charge. The electronegativity value increases as effective nuclear charge on the atomic nucleus increases. Oxidation state. The electronegativity value increases as oxidation state, that is, the number of positive charge of the atom increases. Lastly, hybridization state of an atom in a molecule. If S character in the hybridization state of the atom increases, electronegativity also increases. This table shows the hybrid state, their S character and electronegativity. We can very well see in sp hybridization state, S character is maximum, that is 50%, and is more electronegative. Hence, we can conclude more the S character in the hybridization state of an atom increases, the electronegativity also increases. In periodic table, let us see the trend of electronegativity. As we move from left to right in the period, the electronegativity increases. As we move down from top to bottom in the graph, electronegativity decreases. This is the trend of electronegativity in periodic table. Electron gain enthalpy, electronegativity. Let's try to differentiate between electron gain enthalpy and electronegativity. Electron gain enthalpy, it is the tendency of an atom to attract outside electrons, whereas electronegativity is the tendency of an atom to attract shared pair of electrons. Electron gain enthalpy is the property of an isolated atom, whereas electronegativity is the property of bonded atom. Electron gain enthalpy is the absolute electron attracting tendency of an atom, whereas electronegativity is the relative electron attracting tendency of an atom. Electron gain enthalpy has unit kilojoules per mole or electron volt per atom, whereas electronegativity has no unit. Valence electrons. The electrons present in outermost shell are called as valence electron. We can see the configuration of an element 1s2, 2s2, 2p2. Let us identify this element. It's carbon. In this, we can see that in the outermost shell, there are 4 electrons, and these are known as valence electron. Periodicity. In period, on moving from left to right, the valence electron increases from 1 to 8, whereas in group, on moving from top to bottom, the valence electron remains constant or same. This can be well understood from this diagram. When we move from lithium to neon, the valence electron increases from 1 to 8. Whereas when we move down in the group, that is, if we take the case of group 1, hydrogen, lithium, sodium, they all have one valence electron in their shell. That is, it remains same or constant in the group. Valency of an element is the combining capacity of an element. We can say that the number of hydrogen or halogen atom or double the number of oxygen atom which combines with one atom of an element is taken as its valency. According to electronic concept of valency, the number of electrons which an atom loses or gains or shares with the other atom to attain the noble gas configuration is termed as its valency. Periodicity. In period, the valency increases from 1 to 4 and then decreases from 4 to 0 on moving from left to right. In group, the valency remains constant or same from top to bottom. Electropositive or metallic character. Tendency of an element to lose electrons and form positive ions is called electropositive or metallic character. This character, that is electropositive or metallic character, depends upon ionization enthalpy. The elements having lower ionization enthalpy or energies have higher tendency to lose electrons. Thus, they are electropositive or metallic in their behavior. Alkali metals are the most highly electropositive elements due to their bigger size and lower ionization energies. Periodicity. In period, the electropositive or metallic characters decreases from left to right. In group, the electropositive or metallic character increases from top to bottom. Electronegative or non-metallic character. The tendency of an element to accept electrons to form an anion is called its non-metallic or electronegative character. The elements having high electronegativity have higher tendency to gain electrons and forms anion. So, the elements in the upper right hand portion of the periodic table are electronegative or non-metallic in nature. Periodicity. In period, electronegative character or non-metallic character increases from left to right, whereas in group, the electronegative or non-metallic character decreases from top to bottom on moving in a group. Reactivity of metals. As already discussed, the metallic character increases down the group and decreases across the period on moving from left to right. Periodicity of reactivity of metals. In period, the tendency of an element to lose electron decreases. So, the reactivity of metals decreases from left to right in a period, whereas in group, the tendency of an element to lose electrons increases. So, the reactivity of metals increases from top to bottom in a group. Reactivity of nonmetals, as already discussed, the non-metallic character increases as we move from left to right in the period and decreases as we move down from top to bottom in the group. Its periodicity. In period, the tendency of an element to gain electrons increases. So, the reactivity of non-metals increases from left to right in a period, whereas in group, the tendency of an element to gain electron decreases. So, the reactivity of non-metals decreases from top to bottom in a group. Anomalous properties of second period elements. Reasons are small size, large charge or radius ratio, high electronegativity, non-availability of d orbitals in their valence shell. Lastly, the first member of each group of p block elements display greater ability to form p-pi multiple bonds to itself. For example, carbon-carbon double bond, carbon-carbon triple bond, oxygen-oxygen double bond, nitrogen-nitrogen triple bond, and to the other second period elements, that is carbon-oxygen double bond, carbon-nitrogen triple bond, nitrogen-oxygen double bond compared to the subsequent members of the group. Now, we can see that there is some relation in the properties or the similarities in the properties of lithium, magnesium, beryllium, aluminium, boron and silicon. Lithium, beryllium, boron, they are the members of group 1, 2 and 13 of second period, whereas magnesium, aluminium, silicon are the elements of group 2, 13 and 14 of third period. And this relation is known as diagonal relationship. The similarities in the properties of definite pairs of diagonally adjacent elements in the second and the third period of the periodic table is called diagonal relationship. The reason for diagonal relationship are similar atomic size or ionic size, similar electronegativity, similar polarizing power. So, the pair for diagonal relationship that we need to remember are lithium, magnesium, beryllium, aluminium, boron, silicon. We will sum up what we have learned about the periodic properties with the help of this table. You can see the variation of properties like electronic shells, valence electron, electronegativity, ionization energy, electron affinity, metallic or non-metallic character across the period and down the group. This long form periodic table has certain merits and demerits. The merits are, it is based on atomic number. Position of elements are related to electronic configuration. Periodic properties shows gradual variation at a regular interval. It's easier to remember, understand and reproduce. but at the same time demerits are also there. Position of hydrogen is not satisfactory, fails to accommodate inner transition elements within the same periodic table. Few elements are not arranged according to their electronic configuration. Nomenclature of elements with atomic number greater than 100 can be done by using following rules. Number 1. The name was derived directly from the atomic number of the new elements using following numerical rules. From this table, we can see there are digits starting from 0 to 9. Root, for 0 it is nil, for 1 un, 2 bi, 3 tri, 4 quad, 5 pent, 6 hex, 7 sept, 8 oct, 9 n. Abbreviation is the first letter of the root. N for nil, U for un, B for bi, T for tri, Q for quad, P for pent, H for hex, S for sept, O for oct, and E for n. The numerical roots corresponding to the atomic number are put together and IUM, EM, is added as suffix. Thirdly, the final N of ENN is omitted when it is written before nil. That is, ENN plus nil is equal to NL. Similarly, the final I of BI and tri is omitted when it written before IUM. That is, BI plus IUM, it becomes BIUM by M. TRI plus IUM, one I will be dropped, it becomes trium. The symbol of new element is derived from the first letter of the numerical root, that is, using N, U, B, T, Q, P, H, S, O or E as per the atomic number given to us. Let's take an example. The atomic number of element is 120. There are 3 digits 1, 2, 0. In order to write the name, we have to use the root. Un for 1, bi for 2, nil for 0 with suffix IUM. The name becomes unbinilium. Now, to write symbol, we will use the first letter from the root of the digit. In case of 120, 1, 2, 0, the letter U from un, B from bi, and N from nil. Hence, the symbol becomes UBN. From this table, we can see the names of elements from atomic number 101 to 118 as per IUPAC nomenclature and the official name that has been provided.